sure today it catches. And you know I'm here. I want to change the background. Doesn't look good. Should go to the universe. Is that more simple? Okay. Okay. So. Okay, let's start about the organic reactions. I hope that everybody can see my screen, and I'm going to the full screen mode. So, I'm going to the full screen mode, so I cannot see your chat box. If you have any question, please ask. Unmute yourself and ask. The organic compounds that we have learned so far, that hydrocarbon, carbon and hydrogen, that consist of carbon and hydrogen, mainly carbon backbone, hydrocarbon backbone, and then there will be some substituted groups altogether. The important thing is not only the formation of the hydrocarbons or the chemicals, but also the groups, right? And the most important thing is we want to know the reaction. What does it do? How does it react to our desired product? Or how we can get the most out of it by having some reaction on it. So to know the reaction, how it happens, we have to know the reaction of them. And that is why the reaction pathways are important for these the compounds that you have learned. We will, for this lecture, we will go through this, the reactions for all those very briefly. It is just a pinch on the sea water, like a little bit only. There are out there so much of that organic reactions going on. Okay, by the way, all the reaction that goes in our body, in the cell, are organic reaction. Okay, so the learning adjective for this is that we will typically describe the reaction in alkanes, alkenes, chloroalkanes, alcohols, carboxylic acid, and I'm sure that you all know by now what does it mean, right? Alkane, alkene, chloroalkanes, alcohols, carboxylic acid. So carboxy group, alcoholic group, then chloroalkane, that means when chloroalkane or haloalkane also can be said. Haloalkane means when there is halogen is substituted to this hydrocarbon group. Okay. And then we'll identify the type of reaction. Why is it important for identifying the type of reaction? Because there are billions of reactions in the nature, and we cannot, impossible that we will learn one by one everyone. So what do? You categorize it, right? I mean, chemists, they categorize it so that they can study in one category thousands, millions of reactions. So that is why we have to understand the type of reaction that is going on. Naming reagents and condition. All the reactions that is happening under some circumstances, or that is called the condition for the reaction to occur. Okay. It is, although sometimes in the book we see that A plus B producing C, but it is the generalization of the reaction that is occurring. We do not say, it is not specified under what condition the reaction is happening. Sometimes, even if the reactants are mixed together, the reaction does not occur because the condition is not provided. And that is why the condition is important to know as well. Of course, then what is the product is forming, how do they look like, or what are in them? We have to know that by drawing the structures of the product that will be forming. And then we will identify the structures of alcohols and carboxylic acid that produces esters. And in the next lab, the upcoming lab, actually will be producing esters, and then it will be quite much of you will see fragrance. It's called fragrance, is it? Okay. So organic reactions, just like in organic reaction, there are three different types: the substitution, addition, and oxidation. So substitution, that means we have seen it before in inorganic reaction that C is substituting B or B is substituted by C, and then there's a new product forming, right? This is the way the new product is forming. Hydrolysis is one of those type of reaction. Addition reaction is just being added. Addition reaction, however, is okay. Addition reaction, that one thing is two things are added together. Of course, that is the addition reaction. So substitution and addition, there are difference between them is in alkane. If you remember, alkane means there is no carbon-carbon double bond. There is always one bond. There's saturated. That means alkane. So alkane and alkene. Alkene is carbon-carbon double bond, right? So there is a double bond between carbon. So alkene, it will go for addition reaction mostly, and for alkane it will not go for addition reaction. There is no other way that only substitution will occur here, right? To some extent here substitution occurs, but that is very minimal. On mostly the addition reaction, because of this double bond. Double bond means the electron density is more in there. And oxidation reaction, of course, the oxidation reaction, when there is a chance that oxygen atoms can be infused into it, then produces the oxidation reaction. Okay, so the alkanes. I mean, alkanes will go for this substitution reaction mostly because the carbon-carbon single bond is non-polar in nature. So it's non-polar. That means they are in peace. They are stable. You cannot make any hole into that is stability. But once it is being substituted, to some extent, one hydrogen from that chain has been substituted, then it becomes vulnerable. Okay, and many other reaction can be done. So one of the reaction, the substitution, is like a combustion reaction, and this is the reaction that we are always looking when there is the fire, that our gas, our gas stove is doing, or it is internal combustion engine or a gas lighter. So this is the combustion, reaction is going on inside that. All right, so this is the alkane. Of course, we understand from their structure or the formula CnH twice N plus 2. So we understand that this is a saturated hydrocarbon and oxygen. But the good thing is there can be different type of alkanes, right? CH4, that is an alkane. CH4 is an alkane. C2H6, this is an alkane as well. Then C3H8, it is an alkane. In this way, we can make different alkanes. The chain we can increase. So it depends on the number of oxygen will also change. Depends on what type of alkane or what is the alkane there we are doing the reaction. So you can hear me, I think, yeah. So this alkane and oxygen is reacting with these alkanes in a stoichiometric ratio of, this is the formulas, 3 plus 3 over 2 types of N, that is the same number of carbon, plus half, that is the total number of oxygen molecule will be required, depends on what type of alkane it is reacting. So if we know, or if you remember this number of oxygen, the stoichiometric ratio, the formula for the stoichiometric ratio of oxygen, then it is easier for us to find out what is the number of moles of oxygen required. Anyway, so sorry. Hold on, yeah, I need to play this. Okay, all right. So sorry for the things. And then this is the combustion is going on, but it is not like if we mix oxygen and these gases, it will burn or it will there be fire. The thing that we need is to overcome the activation energy, and that activation energy is overcome by ignition. Just a little bit spark, right? A little spark, one single spark that explores everything. So that is the activation energy that is required for that is the condition for this reaction to occur. Otherwise, you will have in a container all the oxygen and this methane or ethane gas. There will be no fire. But of course, it is very much dangerous. Any single spark will make it to go exploded. So from there, we see, okay, from there, for this reaction, when the combustion occurs, that this is one-way reaction, and then it produces carbon dioxide and water vapor, right? Okay, this water, due to this water vapor, is cooling vapor, we get less amount of heat, but if we can condense it down, we get more heat, but that is different thing, just for your information. I say, okay, so this is combustion, and then the hydrocarbon is getting totally destroyed, producing carbon dioxide and water vapor. So there is no more hydrocarbon left here. But if we can substitute one hydrogen from this hydrocarbon, right? One hydrogen, like this is carbon is bonded to another carbon, then it is bonded to another carbon, and this way it is continue, right? It goes. It can be big chain or it can be small chain, depends on what is the hydrocarbon we are talking about. But let's say this is hydrocarbon, butane. All right, this is all there are hydrogen here. Everywhere there are hydrogen. So what happens is, if I can remove one hydrogen from here, right, one hydrogen, and then I replace this hydrogen with a chlorine, what happens is, it becomes a chlorobutane, right? It becomes chlorobutane, chloromethane, chlorobutane, propane, or it can be bromine. Not only chlorine, because we know halogen are fluorine, chlorine, bromine, and iodine. Fluorine is a very electronegative and it's although small, but very electronegative, and it is very, very choosy. All right. And it does not, it is a little bit difficult for fluorine to incorporate fluorine into that, and because the structure will be a bit more unstable if fluorine is here. Chlorine is good, bromine is good, but iodine again, iodine is a very big molecule. You know, iodine is how many electrons are there? I forgot actually. And the iodine is 53 electrons. So it's a very big molecule. And if it is there to accommodate, it also becomes very rigid and then becomes prone to be broken down, the structure. So, but they are capable of being used in this type of a reaction. So when the chlorine, so X becomes fluorine, chlorine, bromine, iodine. Fluorine does not usually do not react in this way because difficult. But yeah, this is the thing. So once I remove this hydrogen and replace it with chlorine or bromine or iodine, what it becomes is, it is not in good terms or not in a stable state, just like what hydrogen and carbon was, right? Hydrogen and carbon, they are very good, close to each other, and then the electronegativity difference is not that much, so they are producing not ionic bond, covalent bonding, and that is why they are not electronegative. But when chlorine, bromine, or iodine is going there, the electronegativity increases and become electronegative. And since electronegative, so we can do a lot of reaction out of it now. So this is a hole that has been made into the fortified wall of that hydrocarbon, which is very much stable, right? So this is how we can bring it to get more reaction out of this hydrocarbon, stable hydrocarbon. But this is also not a very, what do you call it? That reaction is not occurring as it is. Automatically, you have to have some UV light or heat. So if this methane and chlorine in a box or in a reactor and keep it in the dark for a long time, there will be no reaction. Nothing will happen. But as soon as there is a little get of the sunlight, because sunlight has the UV or UV light, or you give a little bit of heat, it is an explosive type of reaction, and then it produces heat and the reaction occurs with a bang. So this is the condition that it should have UV radiation or heat. Okay, so substitution reaction of alkanes, and this is the substitution reaction. This is not a combustion reaction, and this is not a addition reaction. This is a substitution. The halogen is substituting the hydrogen atom there, all right, in the molecule. So the substitution reaction occurs in this way. It's in front of light. This is methane, ethane, propane. Oh, another question it asks that there are chlorine is diatomic molecule, right? Diatomic molecule. That means there will be two atoms in the molecule, or we can write for our simplicity or for our more clarification, Cl and Cl, right? Cl and Cl. Okay, so this is a chlorine molecule, and then this is 1, 2, 3. So methane, ethane, propane, right? This is a propane, and this propane, this 2 chlorine will go to this propane. Where does it go? Where will it go? Which hydrogen will it go? Will it go to this hydrogen, remove this hydrogen, it will remove, or this hydrogen it is remove, right? Now one thing is this 1 and 3 carbon is similar. Both are from either end, right? Both are from either side, and the 3 hydrogens are on the 1 and 3 carbon are similar to each other. So we cannot differentiate. There is all atoms that looks like the same. So we cannot differentiate these 3 hydrogen. So 1 chlorine can go here. That means this chlorine, if it goes here, it is same as going to this carbon or this carbon, right? It is same because all these 3 carbons are same, hydrogen are same. And since it is same, this is also same as going though to here, this hydrogen, because this hydrogen and this carbon, there is no difference between them. So it will be considered the same thing going to this hydrogen as well. But there is a difference because this 2 hydrogen is different. This carbon is different from 1 and 3 because this is in the middle, right? Both of them either. This is the middle. So these 2 hydrogen will be different from this hydrogen because of their position, not because of their atom look like, but because of the position, because this is the middle position. So 1 chlorine will go and react to this hydrogen, which is similar to 1 AB. This hydrogen, this hydrogen, this and this hydrogen, this all the same. It replace it here, replaces the same. And another chlorine will go and replace this hydrogen. This hydrogen and this hydrogen on the second carbon is the same thing. So it will replace these 2, either of them. But the thing is, it is happening in a not on the single molecule, on the single methane propane, but in a separate way. So 1 chlorine is going and producing this type, and another molecule is being produced is this type. It is not from the same carbon. Like in one molecule there's two chlorine. It is not happening in that way. Okay, so why it is not happening? There is another different things, but we will not be discussing here. All right, so this is how the reaction is, a chloroalkane is being produced. So when this chlorine is there, the chlorine is attached to this carbon. What is happening? Chlorine is electronegative, right? We know from the from the chemistry knowledge that electronegativity series. We know from the electronegativity series that fluorine is the most electronegative. Fluorine is the most electronegative. Then oxygen. After that is chlorine. After that is bromine. After that is iodine. In that way it goes. The electronegativity. So chlorine is more electronegative than hydrogen or carbon. So what will happen is electronegative means it attracts the electron towards itself. So its happiness is more electron will surround it. That is its happiness. So it will attract, and it is capable, and it will attract more electron. More electron means in this bonding there are two electrons, right? Two electron makes one bond. So there are two electrons in the bonding. So what this chlorine will do is it will try to draw both of the electrons towards it. And thus carbon will have less electron shield on it, or maybe it will be feeling deficit of electrons, and that is why so the more electron goes to chlorine side, right? More electron goes to chlorine side, chlorine becomes partially negative, and carbon becomes partially positive, and that is why it becomes polar. This bond is polar. It is this side is not polar because hydrogen and carbon, they are not drawing electron from each other. They are sharing the electron, but chlorine is very much capable, is drawing the electron towards it, and then it becomes polar. Since it becomes polar, what will happen is it will draw the electron more towards it, and thus the electron, the charge density started. Okay, the charge density started, and since it is different, positive and negative, so what will happen is this carbon, since it is positive, more negative ions, let's say hydroxyl ion is a negative one for this case. So negative ion is, okay, I'm just, the hydroxyl I'm showing is just for an example, I'm going with. So since it is negative, it will go for a positive one. It will look for a positive side to attack. So carbon becomes more vulnerable now, or prone to be attacked by negatively charged. So that is called nucleophile. The negative ion that look for the nucleus, or nucleus is positively charged, right? So look for the nucleus is called the nucleophile. And that is why the reaction becomes much more easier now for the hydrocarbons. So this chloroalkane now will go for reaction sodium hydroxide, whereas the hydrocarbon, if there is just a saturated hydrocarbon, there's propane will not do any reaction with sodium hydroxide, no reaction. It will not produce any reaction with sodium hydroxide if it were just a propane, right? But since it is chloroalkane, right, it will be reacting with sodium hydroxide because of this chlorine molecule, chlorine atom here. And this hydroxyl will be replaced, chlorine will be replaced by this hydroxyl, and chlorine is coming up to produce a salt, which is sodium hydroxide. So chloromethane, chloropropane, chlorobutane, chloroethane, everything will do the similar type of reaction. So we do not need to remember chloropropane, chlorobutane, octane, chlorodocan, whatever. As long as it looks like chloroalkane, right? It will react with sodium hydroxide in this form, and then they will produce an alcohol, which depends on the main hydrocarbon chain, and then the sodium chloride. If it is not chlorine, if it was bromine, if it were a Br, or if it were a sodium iodine, right? So it will produce sodium bromide or sodium iodide, depends on what is available there, right? So this is how the reaction, that is how the reaction, I mean, we can get the reaction going just by doing the substitution reaction. So now it will also react with ammonia. Ammonia, by the way, we know that ammonia looks like this. There are 3 hydrogen attached to it. This hydrogen 1 here, hydrogen 1 there, and another hydrogen like, let's say here. So 3 hydrogen makes a base. 3 hydrogen makes a base, nice triangle base. But nitrogen is still got 1 electron, 1 pair of electron on the top. So since this nitrogen becomes, this molecule becomes a little bit polar. So it will react with this halo or chloroalkane, and then amine will be produced. Amine will be produced in this way. 1 hydrogen more will be replaced from this ammonia, right? 1 hydrogen will go out from here. 1 hydrogen will go out from here, and that hydrogen will produce HCl, right? So this is how the reaction goes. This is a chloromethane. If it is a chlorobutane, chloropropane, hydrocarbon, it will produce with ammonia. It will produce the same. The 1 amine it will be produced, but when it is only chlorine is there, you know, I'm talking about chloromethane, chloropropane, chlorobutane, chloropentane. But if there is any other groups is attached, any other prefixes attached there, then the reaction will follow. That is different thing. Do you know what I mean? I mean that, let's say this is chloromethane, right? So the reaction will go. If it is a chloroethane, CH2Cl, but there is another, let's say, hydroxyl group is attached in this way. So the reaction will be a little bit different here because there is hydroxyl group is attached again. So that's what I'm saying, that if nothing else is attached to the main hydrocarbon, only chlorine is attached to this hydrocarbon, then the reaction will always be like this. All right, always be like this reaction. Okay, and then this substitution reaction that we have been seeing just now, it will, the mechanism, if we want to know, just to give you a glimpse of what it looks like, how the reaction actually occurring, we just put into the test tube or in the beaker, and then we see that the reaction is going on, but inside there are many things are going on. So one is the unimolecular nucleophilic reaction, substitution reaction, SN1 we say, another is SN2. There should be, S should be in a big capital form, SN1, N capital but subscript, yeah, that's it. So this is a unimolar nucleophilic substitution. Nucleophilic, that you already understand that there is a electrophile which is going to nucleophile, sorry, which is going for the nucleus, which is going for the positively charged, and this reaction occurs in one single step, right? So this nucleophile, nucleophile, this is the negatively charged, will come from like a hammer. It is coming and then hitting it, making some things go away, and then it is holding that position, and then boom, the reaction done. But for the bimolecular reaction, it happens in a very slow position, right? Slowly, it will the leaving group. For this case, this bromine is the leaving group. Actually, this is not a Good example. The bromine is going out, and then there is a chance the bromine is about to go out. There is a chance carbon is sad because it has a more positive. It cannot be balanced, so it's looking for someone which is more negative, so it can balance. And for some time they will sit together, negotiate. The leaving group, this is leaving group. Leaving group will negotiate, it go out, and then the incoming group will negotiate with carbon and for some time, and then the reaction. So this is a two-step process, and that is why it is called SN2 position. The good thing is, or the bad thing, I don't know whether it is good or bad, that this thing will not be tested or it will not be in the exam for you, but it is just to show you what it will look like. I mean, if we try to understand chemistry more about it, or want to know how the reaction is occurring in our organic system or in a real life, so we'll have to understand those things. And there are much more interesting thing actually, more than this here. So just to introduce you about those things. All right, so okay. One example, it says that write equation of the production of chloromethane from methane. Methane, it is the alkane, right? It is an alkane, and you cannot do the reaction. It does not go for the reaction for sodium hydroxide or ammonia or anything. It will not do the reaction. So what you have to do is, but chlorine, yeah, but for haloalkane it will produce with the presence of heat or UV light. Light means UV, yeah? UV light, not any other light. It will not do the reaction. So it will produce the chloromethane, and once the chloromethane is produced, then it is hydroxyl ion. This hydroxyl ion is coming from base. So it can be sodium hydroxide, or it can be potassium hydroxide, or it can be lithium hydroxide. So it is coming and then producing an alcohol on it. All right, so this is once the alcohol is being produced, right? The functional group is hydroxy or alcoholic group, and this group is, since it is alcoholic group, it will be oxygen is there, right? The oxygen is there. Oxygen is very much electronegative next to the fluorine, so it's the second most electronegative element on the periodic table. So what it will do is it will draw the electrons all around it. Okay, all around it, it will draw the electrons. And hydrogen or guy, it will here for this side. Okay, this side. Carbon has many other things. Carbon has one hydrogen, two hydrogen, another carbon neighbor, but this poor guy does not have anyone. So what I'll do is, or I don't know if it's bad or good, but it will try. It is easier for the hydrogen to go away from here because of this too much electron pull by this oxygen. Oxygen will try to too much pull the electrons. Okay, and then the hydrogen feels pity. Hydrogen does not have much electrons, so what it will do is it will just go away from here. All right, because it is not having the share of electron it was supposed to have or it wants to have, so it is just breaking apart. And when it breaks apart, this electron, now oxygen is now having, I mean, it is not octet is filled up. It must have another someone to catch so that it can fill up the octet, become stable, and that is how the reaction will go. And we can see the more substitution reaction for this alcoholic group. So for this ammonia, I mean for this alcohol, the reaction is very much similar to what we have seen for this chloroalkane, right? So this alcoholic group, the reaction is also similar with that ammonia. So it will produce an amine as well. All right, it will produce just like what I have seen before. It will produce amine and water molecule. The one hydrogen is going from here. That hydrogen will group or join this team to produce an water. Okay, water vapor, right? This is not water, it is gas. This is gas because it is the reaction is happening at 400 degrees centigrade. It is not very spontaneous reaction, and in presence of alumina. Alumina is aluminium, Al2O3. Alumina. There is a catalyst. As a catalyst, alumina will be required to have the reaction. So at 400 degrees centigrade only, the reaction will occur. That means this alcohol is not that much. The hydrogen is not always that much. What do you call it? Available to go out. Remember that we were talking about for hydrogen bonding. Does anybody remember what is hydrogen bond? Is there anyone who remembers what is hydrogen bond? Anyway, so we are talking about the hydrogen bonding, right? So since there is a tension between oxygen and hydrogen, and there are many other molecules in the same liquid, in the same volume of the in the beaker or whatever you have, so they are producing a hydrogen bonding between them, right? So it is not like they are always readily going out. They are there, but they are prone to do some reaction, and that is why it will need 400 degrees centigrade and alumina for ammonia to react with alcohol. If you do not provide this 400 degrees centigrade temperature, this reaction is not going to happen. Simple as that. Okay, so this is it. And when the reaction occurs, the product is aminoethane, because this amine is coming to that, and this ethanol is from here. Okay. Now for the alcohol, so oxidation reaction for the alcohol. Oxidation reaction, we have seen that there are 3 different types of alcohols, right? First degree, second degree, and third degree, or primary, secondary, and tertiary. First, second, third, or primary. First degree is primary alcohol. So we already also know the difference between them, what is called primary, secondary, and tertiary. For tertiary alcohol, we remember that tertiary alcohol does not change color of potassium dichromate or potassium permanganate, right? Only first degree and second degree alcohol will do the reaction or change the color of the reagent. So when oxidizing agents are oxidant is that provides a nascent oxygen, right? They can provide a nascent oxygen, an oxygen atom. They can provide. So potassium permanganate is one of them. Potassium dichromate is one of them. There are many others, but let's say that this is the oxidizing agent. So this reaction, if we provide, we do the reaction with in the alcohol, this oxidizing agent, right, with the alcohol in presence of heat under reflux and concentrated sulfuric acid. So 1 drop of concentrated sulfuric acid, and we have to do some heating under reflux. Reflux means there is a, it will boil up and then evaporate and come down when we condense it back. So this is the reflux. The many cycles going out in that way. So this is the reaction will occur, and then it will produce carboxylic acid. All right, it will produce a carboxylic acid. This R means that the hydrocarbon chain, CH3, CH2, CH3, CH2, 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 like that. CH3, then CH2, CH2, CH2. It will go on. It depends on how many, what is the length of carbon and hydrogen you have. It can be CH3 only. Right, it can be CH3, CH2, it can be CH3, CH2, 2, 2, 2, in that long also can be. So this R depends on what type of carboxylic acid. We can call it later, depends on R, but it will be a carboxylic acid. The thing is, does it always need that much of concentrated sulfuric acid and heat under reflux? No. It can, this reaction can occur, but very small amount, very small amount. Without this condition, the reaction can occur also, right? But it is a very small amount that reaction can occur. Okay. All right. So what I was saying that different type of alcohols. How does it happen? What is the mechanism that's happened? This is a first degree alcohol, butane 1-ol, because this hydroxy group is attached to the carbon, right? This carbon has two hydrogen attached to it, 1 and 2. This carbon has two hydrogen attached to it. This is a secondary alcohol because the hydrogen attached to the carbon, hydroxyl attached to the carbon, it has only one hydrogen attached to it. And this is a third degree alcohol because the hydroxyl attached to the carbon does not have any hydrogen, but it is directly attached to other three carbons. There is no hydrogen here, so it cannot have any other replacing. It will replace the hydrogen. So since there is no hydrogen here, the third degree one, it does not have any option to replace anything. So this primary alcohol, this I mean, how do you call it? Oxidizing agent, the oxygen, provided oxygen, it is producing this carboxylic acid. This hydrogen is being removed from here. These two hydrogen are removed from here, right? And one oxygen came in. Let me just. So this hydrogen go away from here. So the carbon has two arms. Carbon has two arms free, and oxygen needs two bond to make. And that is how this bond is being made, and this becomes the carboxylic acid. For secondary alcohol, since there is only one hydrogen to replace, right? One hydrogen to replace. So what will happen is this one hydrogen is being replaced, but this hydrogen, what it will do? It cannot do anything. Hydrogen cannot stay alone as it is. So this hydrogen will bond with this hydroxyl, and then they will produce a H2O, water. And now carbon has two arms free, one from here, one from here. And both of these arms now it will bond with the oxygen to produce a ketone. It will produce a ketone. So first degree alcohol producing a carboxylic acid, second degree alcohol is producing a ketone. Third degree alcohol, there is nothing to remove, so it does not do any reaction. It doesn't bother. Okay. So the first degree and second degree alcohol, that it will do the reactions. So what will happen is potassium dichromate, which is yellow color. Potassium dichromate is yellow color, and with the reaction with first and second degree alcohol, it will produce a greenish color solution. Solution will be green. Okay. If this is the potassium dichromate, I add alcohol to it, any first degree or second degree alcohol, I add to it, it becomes green. Potassium permanganate was purplish color. So if I add some alcohol to it, if it is first degree or second degree, it changes color. It becomes colorless. So this is the way we can find out what is, if the alcohol is first degree or second degree or tertiary. Now alkene. Okay, so alkene, as we know that there is two double bonds between them, and because of this two double bond, there's one double bond means two electron, right? One bond means two electron. Two electron makes a bond. Here is one electron. Here carbon is giving one electron with hydrogen, so there is one bond. Carbon-carbon between two bonds, double bond, means there are 4 electrons involved. Since there are 4 electrons here in this double bond, whereas there is only 2 electrons here, so the electron density for this carbon-carbon becomes too high, right? Electron density becomes carbon and carbon becomes too high, more. So the electron density is high, and now because of this electron density, it will become more susceptible or more vulnerable or more prone to do some reaction, or those are electron deficient, right? Those electron deficient, they can do more react. I mean, they can attack here because the availability of more electrons, they can attack here. Those who are more electronegative means, those who needs the electrophile are halogens. For example, chlorine is one of them, and that is why chlorine, if we need to do the reaction, I mean, if we just keep the reaction, chlorine and alkene, which is double bond alkene, just chlorine and alkene together, it will do the reaction. It will automatically, do the reaction, and at the room temperature. Whereas if you remember the last slide, I mean, just now we said for alkane, we have to keep the chlorine with the alkane plus provide heat or UV light. Only then the reaction will occur. But for this case, it's room temperature, is automatically the reaction will occur. As soon as we mix together, the reaction will occur. And since there are 2 bonds, one double bond, that means 2 bonds are there. This bond will open up, break from here, and then it will open one each. So the chlorine can actually bond to both carbon. So by this way, ethene, from ethane, when there is unsaturation, we call it ethene. ENE is added at the end of the name. So chlorine is reacting with ethene to produce 1,2-dichloroethane. Right? 1,2-dichloroethane, because one chlorine here, another chlorine there. So 1, 2, you can count this one 1, this one 2, or other way is all the same. 1,2-dichloro means there are 2 chlorines and ethane. Characteristic test of alkene. How do we know if there is an alkane or alkene is there, right? So alkene, since it will react automatically with instantly, readily with halogen, right? So this alkane, I mean, what do you call it? If we keep this chlorine into this alkane, I'm saying that, okay, if we keep the chlorine in the alkene, then it will react. But the problem is chlorine, we cannot see the gas, it doesn't have any gas, I mean, color of the chlorine, and it is very dangerous. Right? Bromine as well is dangerous, but the thing, a good thing is we can make the bromine water. We can make it a bromine water by adding bromine to the water, and the water becomes reddish. It's not reddish color, but it is brownish, yellowish color. It becomes. So when in that liquid in alkene, 1 or 2 drop of this bromine water is added like this, this color will fade. It will become vanished. The color is no more there. All right, the color is no more. We will be doing this thing in the lab, okay? But when you use this bromine water, be very careful. You cap it up. I mean, once you have used it, cap it. So don't leave it open. It is not good for our health to inhale. So if we add 1 or 2 drops of bromine water, if it is an alkene, if there is a double bond unsaturation in that liquid or in that compound, it will become vanished. It will be colorless. But if it is an alkane, there will be no change in color. Okay, it will not change. The bromine water will not change in color. It will be still brownish or reddish brownish color. So alkene will only change the color. And just now we have seen that alkene, it will react to halogen at room temperature at any given condition. That is, I mean, in any given condition in the room, it will do the reaction and produce that dichloro or chloro or haloalkane. Actually, it will produce the haloalkane, and then it will produce also with that hydrogen halide, that is alkane with hydrogen, and it can be a gas, it can be liquid. So it is reacting with this alkene at room temperature, again in the room temperature, and then it is producing 1-chloroethane. Now it is 1-chloroethane because there is only one halogen here, only one chlorine here. Previously there was Cl2, right? But now it is only Cl and one hydrogen. So one hydrogen goes to one carbon and halogen goes to another carbon. When this one double bond becomes open, goes to 1 to 1. All right. Alkene, it reacts with hydrogen gas as well, but at 170 degrees centigrade and with the presence of nickel or platinum to make it saturated or make it alkane. From alkene to alkane it produces. Okay, so now, hydrogen. Why needs to have 170 degrees centigrade? It is with with chlorine it readily reacts, but for hydrogen it needs to be 170. For this, the one funny answer is this alkene came out from alkane, right? It was alkane before. We have to remove 2 hydrogen to produce an alkene. From ethane, we had to take out 2 hydrogen to produce ethane. So it does not want to go back to that state again. So that's why you need to force this thing. Another thing is hydrogen is not that electronegative. I mean, hydrogen gas is quite stable. H2 is quite stable gas. It does not need to go and bind with this double bond. It doesn't require that much. But when you force it with 170 and the nickel or platinum catalyst, then only it goes and do the saturated. And this is the reaction actually happens to produce the margarine. Okay, to produce margarine or artificial butter, right? This is the reaction that happens in saturated, unsaturated vegetable oils. Okay. The hydrogen is reacted with hydrogen to produce the saturated fat, and that is how the saturated or margarine artificial butter is produced. Okay, I think I need a 5 minutes break. Afterwards, we'll see some more reaction about the alkane and alkene. And before, during this time, we are doing this waiting for our tea break. We go to menti.com, please. Go to menti.com. All right. Go to menti.com, please, everybody. Menti.com, and now 7477, let me type it here, 7477 7316. This is the code. Please type in and then provide your answer. Okay, I'll share this thing as well with you, slide. Okay, so vote, please vote. What is that? Vote is closed now or what? Oh, vote is open for voting. Yeah, voting is open now, so please go there and vote. Which one do you think is the perfect answer? I'll be back in 5 minutes. Okay, I think I'll stop. I'll start counting. I mean, start counting the countdown. Start the countdown. 1 minute. Please, those who haven't voted. Oh, those who haven't is only 6 of us has voted, only 1 hasn't. So anyway, let me see what is the. By the way, okay, let's the voting be finished first. $25 seconds, 20 seconds actually. Five, 4, 3, 2, 1, done. Right. So let's see. Oh, okay. Two of us, quite good. The spectrum, I see, I like it. 2 of us has said that A is the most polar, or which compound is polar if there are more than one, which is more polar. Okay, so A, 2 of us said A, 3 says C, 1 say A and B, 1 say A and C. It's quite good thing. Let's see the thing. Oh, by the way, what is the name for, what is the group on A, compound A? Can anybody tell me what is the group on compound A? This is CO, this is a keto group, right? This is a keto group. This carbon has two oxygen and it is bonded to 2 other carbon. So this is a keto group. This is, the group is unsaturation, double bond. There is a phenyl group as well, sorry. For A and C, the common group between them are the phenyl group. This is the 6, and the hexagon. That hexagon is the phenyl group. So, let's say that which one will be more polar, right? A is the most polar, should be. I forgot who was. 2 of us say A. Okay, A should be more polar because this of oxygen, right? The oxygen is very much electronegative and it will draw the electron towards it. Of course, this phenolic group is also there is, but it is much stable because the electron, we'll see much of it later on. The resonance is going on, so it is much stable. But since due to this CO group, okay, it is, the oxygen is drawing the electron towards it, so it is much polar. It becomes polar. Whereas B is also a little bit polar because there is an electron density between carbon and carbon, the double bond. The electron density is here, so there is a tension, or you can say that there is a more electron is dumped here or group up here, so that it becomes a bit more negative than the rest, and that is how the polarity goes. But for C, there is no polarity here. I mean, it will be not polar because this carbon has 2 hydrogen attached to this carbon, right? And these 2 phenolic group, they're quite stable, they're okay. So there is no tension between any carbon or hydrogen or any phenolic group. So there is no electron density or electron tension or electron pull towards any of them. It is nicely distributed because there is no groups, no oxygen or chlorine or fluorine or iodine or any sulfate, nitrate, hydroxyl, carboxylic group. When these type of groups are attached to that part, it will become more electronegative because the electron pulls towards them is much more than just like, I mean, simple carbohydrate. So C is not that, electronegative. C will be there. A and B will be more. Of course, A is more than B, and in both cases, A and B we can say. Okay, so I hope that it helps for you guys. I put A and C. No, it should be A and B actually. Not A and C. A and C. Okay, so let me just stop it here and go back to my lecture slide. Okay, so we were here. Now let's go to all right. So now alkene, when it reacting with water means water gas, of course, vapor, water vapor. So alkene, which has a double bond, right? Alkene has a double bond. It is reacting with water molecule. It's reacting with water molecule, water vapor at 300 degrees centigrade and concentrated sulfuric acid in presence of sulfuric acid and concentrated 300 degrees centigrade. So it is quite much actually, that 300 degrees, and again is sulfuric acid, phosphoric acid. H3PO4 is a phosphoric acid, by the way. So only then it will produce alcohol. But if we could react, okay, before that, let's finish this one. So this is an alkene. Water molecule is vapor, is reacting, producing alcohol, and the main backbone remains the same. Only one hydrogen is removed from one one carbon, right? From here, one hydroxyl is attached to this, and this carbon, the hydrogen is going to attach, or vice versa. Okay, so this is how this hydration or alcohol is being produced. So my point is that you see that 300 degrees centigrade is required with phosphoric acid as a catalyst. But if we had chloroalkane, right? If we had chloroalkane and we used sodium hydroxide that we have seen previously, like I don't remember, probably in 15 or yeah, slide number 15 or something like that. So chloroalkane and sodium hydroxide or potassium hydroxide, it produces alcohol as well without any heat or any catalyst. So that is much more feasible, because 300 degrees centigrade, consider that you have to produce few hundred tons of alcohol every day, and 300 degrees centigrade you have to elevate the temperature for this. It's too much of energy you will need to burn, and also catalyst not much, but still you have to catalyst and then later you have to clean it off. So this is more troublesome than the previous way that we do it, haloalkane, right? And then with the help of a base alkali we can produce. All right, so if we add ACl, acid, to this alkane, then what happens is this, of course, it is getting broken or opened up, and one chlorine is going to attach, one hydrogen is going to attach to either side of that double bond. So hydrogen can attach here to this carbon, or hydrogen can attach to this carbon. There is a rule, there is a theory in organic chemistry, that Markovnikov rule, which says that it will bind, the hydrogen will bind to the carbon where it has less number of hydrogen. Okay, so this carbon has only one hydrogen, so this hydrogen will usually bind to this. But this will be like 85% or 95%, right? And this will be 10% or less this time. But still there will be this type of product will be formed. and both will be formed, but it will be 85% product. And there is anti-Markovnikov rule as well. When there is a strong oxidant present, it will just reverse. So we will not discuss much about it later probably. Okay, so another example of when water is added in presence of phosphoric acid, right? And of course with in presence of heat as well. There will be heat added into this reaction. So this is how this alcohol is produced. If the reaction, I mean, if in the exam we ask you that how the reaction is producing, show the structure of the product. So we have to come up with this product. Show the product as well. You have to. All right, so now we are moving towards the polymerization. Polymer is one of the most used material in the world right now at this moment that you are looking at towards your screen. 90% probably of it is produced of polymer. So polymer is actually I don't know, you can call it a bliss or it's a curse. Depends on the usage or our ethics that we are using it. Okay, so this is the polymer and how the polymer is produced. Ethene or propane, when there is an unsaturation between them. So the unsaturation of this is saturated. We produce this by it is made saturated by adding hydrogen or any other element, and this chain is very long chain, 20 to 30 carbon in one chain. All right, so then it is called very long chain of carbon hydrogen carbon hydrogen carbon hydrogen in this way, right? Carbon hydrogen in this way. So this is a very long chain. Consider that there is 1 2 3 4 in this way 30 or 40 or 30 carbon, right? So we have to draw a very long. So actually this is long. This is polyethene. So from polyethene to becomes polyethane when we add hydrogen and with some adding of catalyst. And this is the same molecule or same material that we use for our plastic bag. That is, I mean, polyethane is the plastic bag that you use, shopping bag, right? So that is the simple example of polyethene. And you know that polyethene is so, I mean, it is soft. You can bend it, you can fold it, you can make it whatever shape or size. You can blow and make it a balloon. So you can make it polyethene because it has only carbon and hydrogen, but it's a long chain, so they are intricately in the interwoven thing and that makes a polyethene. Okay. Now, if it is not only hydrogen, if I just replace one hydrogen with one chlorine, right? So this is the vinyl chloride, just like the ethene. If there is a chlorine there, we just, what do you call it? Just replaced with chlorine is the vinyl chloride. And then this chain is also very long. This chain is also very long. And this one double bond opened up many other, the same type of molecule attached together, the same units. This is called the unit of this polymer chain. This is the one single unit, just like a building block. This is a single unit, of course, in the presence of catalyst. So when they are attached together, 30, 40, 100,000, so they call the polymerized, polyvinyl chloride, also polychloroethane. All right, so polychloroethane, and just because of this chlorine, it is hard. It is hard, and that is why we produce with this polychloroethane, we can produce this type of product, the heart shaped, we need the heart shaped one, all these things. Depends on how much chlorine is into that molecule. So you can see the difference between just one chlorine atom and one hydrogen atom, right? So when there is a hydrogen atom, it is very soft. It's a polymer bag, plastic bag, you can see. But when the one hydrogen is replaced, it can be as hard as this plastic. It can be a plastic sheet actually that we can make the table as well out of it. So this is the difference between one atom. Okay. So example 2 says that outline the reaction pathway to convert 1-chloropropene to propane 1-ol. All right. So the reaction is asking us that how can we from here, we can make this, right? From here, we can make this. What is the difference? One hydroxyl goes there, and one hydrogen goes here. And of course, since this, so it has to be broken. Otherwise, there is a 5 bonds to carbon there, which is wrong. So propane 1-ol, how do we produce this from here to here? Oh, it looks like O, but it is not an O, of course. Okay, so how can we? So it is simply, we know that we need one hydrogen, one hydroxyl, and from there we can we know that 2 ways we can produce. That is, one, we can add hydrogen and the chlorine to it, so that the hydroxyl will attach to this thing, that heat, and hydrogen, we attach hydrogen gas in presence of nickel, so that the hydrogen is attached to both. Or if we add water vapor in presence of heat, right? In second step, sorry. So first step is heat and water, hydrogen, so that hydrogen is attached to these 2 carbons. And second step, we add water, so that this chlorine is replaced by this hydroxyl ion, and then produces the desired product. Okay. Example 4, it says that complete the reaction pathways of butene, but-1-ene or but-1-ene, actually there is no other way, 1-butene, yeah, 1-butene by giving reagent condition or organic product to the reaction. The question is asking that we have this at the beginning, but-1-ene or 1-butene. So from there, how can I get this 1,2-dichlorobutane and also butane? This is saturated. And another reaction is asking that if we put water, gas or water vapor in presence of solid sulfuric phosphoric acid catalyst, what will be here and what will be here if this is the condition applied given to them, right? So from this reaction, we see that it is a 1,2-dichlorobutane. 1,2-dichlorobutane, that means this is unsaturated. If I add 2 chlorine, chlorine molecule or 2 chlorine atoms together, of course 2 chlorine atom will produce a chlorine molecule. So it will produce 1,2-dichloromethane, butane. So this is butane, right? 1, 2, 3, 4. Yeah, this is butane, but-1-ene. So 1,2-dichlorobutane will be produced. And then it is a butane, it's been produced. So what will happen is, if we just add hydrogen gas at 170 degrees centigrade in presence of platinum, right? In presence of platinum catalyst, then it will produce butane gas. When there is water and sulfuric acid as given, so in presence of phosphoric acid, water vapor, it will produce alcohol. So it will produce butane 1-ol is there. Okay, it is for butane 1 all or 2 butane as well. So the hydroxyl is going to attach here and attach there as well. So hydroxyl is going to attach both position, both carbon. If we count, this is 1 carbon, this is number 2 carbon, this is number 3 carbon, this is number 4 carbon. So this hydroxyl, it will not discriminate carbon 1 and carbon 2 because none of them are distinguishable. All are identical, so it doesn't discriminate. It will bind to all, but not in the same molecule, in the different molecule, and they will produce not 50-50, but 40-60, something like that. And if we add HCl in presence of aluminum chloride, so it will produce the chloroalkane, chloro 1 chloro and 2 chloro both, just like hydroxyl that it attaches to both of the carbon. The chlorine will be attached to both of the carbon as well. Okay, now the functional group. This functional group is a carboxylic group. All carboxylic acids are weak acid, thus ionized partially in the water that we have seen before. The ethanoic acid or acetic acid we have seen before, right? And carboxylic acid undergoes acid-base reaction and condensation reaction. So this is the carboxylic acid. How do we know if there are two liquids? One looks like carboxylic acid, one looks like any other water. So how do we know that this is a carboxylic acid and this is water? Well, do we need to drink? If we drink, can we tell this is a carboxylic acid and water? Never do that, first of all. And the second thing is, we should react with sodium carbonate or sodium bicarbonate as well. The effervescence, tomorrow we will, in the next lab, coming lab, we will see this thing as well. So the effervescence will happen. That means the bubble will come up from the liquid. When the bubble comes up, we know that this is carboxylic acid. Water will not produce this thing. The bubble comes up and then it produces sodium ethanoate. Right. This produces sodium ethanoate. The hydrogen is going away from here and sodium is going to attach to this oxygen. So this is sodium ethanoate from ethanoic acid. It depends on what. If it's a propanoic acid, sodium propanoate. If it's butanoic, sodium butanoate. In that way, it will be produced. And this is salt of sodium. Oh. The main thing, the carbon dioxide will be released. Because of this, the carbon dioxide from here it is released, and this is producing the bubble or gas. So this is the carbon dioxide actually. It's coming out from the liquid. Carboxylic acids also react with alcohol and produces ester. But it needs a heat under reflux, concentrated sulfuric acid as a catalyst. Without it, it will produce, but not that much amount. And all ester, it will have some smell or flavor, is it called? Or some smell it will have, characteristic smell. Different esters will have different flavors or smells, right? How does the ester form? This is a carboxylic acid. This is an alcohol. R means, the CH3, as I said, R means CH3, CH2, CH2. These two R can be same. These two R can be same, or they can be different. Same or different. Both way it can. It doesn't have to be the same R, or it does not have to be same and different R. It can be same or it can be both. Okay. So when this ester and this alcohol is reacting, this OH, both of them has OH in that. So from this OH, what will happen is this hydroxyl will go out from here, and this hydrogen from here, it will go out and it will produce water from there. It will produce an water. No, sorry. This hydroxyl will go out from here, but from here only hydrogen will come. Okay, so they are producing water by this way. And this oxygen is meeting with this carbon in this way. So this is ester bond is being formed. This is the ester bond is being formed by this way. Okay, so this is an ester. For example, ethanoic acid, which is a acetic acid, and ethanol. So both CH, this R are the same. So ethanoic acid and ethanol, when they react together, they produce ethyl ethanoate. Remember the name for an ester, the alcoholic part comes at the beginning. First, the alcohol's name comes. It came from ethanol, so ethyl. This ethyl part comes from ethanol. So ethyl ethanoate, OATE, is added at the end of the name. Propanoic acid and ethanol. So ethyl propanoate, it will be produced. Only it's very easy to produce. The same structure, everything remains same. This hydroxyl and this hydrogen go away. The oxygen is attached instead of this hydroxyl. So ethyl ethanoate will be produced. Esters are the physical properties of the esters are a low molecular weight, small molecules, are volatile and smelly. Not all esters has very good smell. Some of them has pungent smell as well, but mostly are good. And then they have low boiling points that allow them to evaporate easily. Esters with larger molecule size and oils are waxes and bee waxes. So in the beehives, there are a lot of waxes, esters actually. And also you see, the honey that in the morning you will take for breakfast, much of it is the ester as well. Chemical properties is made by condensation reaction, usually undergoes hydrolysis reaction. Of course, the water goes away. If you put more water, it will be hydrolyzed. In acidic condition, it will break down to the original form, carboxylic acid and alcohol. And in alkaline condition, forms carboxylate salt and alcohol. So acidic condition, it produces carboxylic acid. In alkaline or basic condition, it will produce a salt, right? We need to remember this thing as well. Okay, so we will see many of these, I think 1, 2, 3, 4, 5. I think we will see 5 of each in the next lab, or we will produce 5 or 6 of them in the next lab. So esters, they have characteristic smell or flavor. And much of the flavor, ice cream, the tea or the drinks that we eat mostly are from these esters. Although, of course, they are, safe to eat, and that is why it is a food. But, I would go for the fresh orange. Okay, so structure of few esters. This is the structure. When this is a line structure, schedule structure. At the end of the line, there is a CH3. At the end of the line, there is a CH3. Okay. At the end of the line, there is a CH3, unless otherwise it is stated something else. This is CH3 as well. At the end of the line. And in between, at the corner of this is C, carbon. There is a carbon and hydrogen, 2 hydrogen, of course, because there is 1 bond, 2 bond. This hydrogen, carbon will have 2 other hydrogen. So this is the general rule. And this is an esters, and they have this type of characteristic smell. This is raspberry, isobutyl formate, apple, butyl acetate, pineapple, ethyl butyrate. Ram, propyl isobutyrate, peach, benzyl acetate, orange, octyl acetate, and wintergreen, I don't know what is this, honey, methyl phenyl acetate. So in the fake honey, quite much of these things are used. Strawberry, ethyl, methyl, my goodness, this is quite big name. Okay, so this is the things that the esters are. So the sum of the reaction of the esters. So it has been produced by the condensation, right? The water goes away from it and the ester is being produced. So it will also become dissociated in presence of water and produce a carboxylic acid and alcohol. But when there is a hydroxyl or a base, sorry, so it will produce a carboxyl salt and alcohol as well. So yeah, heat and another reflex, it will produce different product in different things. And this is the reaction that it will produce. The ester is broken from this hydroxyl as same position where it was attached. At the same position, it will get the broken down. So some of the examples here that esters will be reacting with the water and producing carboxylic acid, propionic acid, and ethanol. But if it is a base, sodium propanoate, the sodium ion is coming next to it. So this is sodium, yeah. Sodium, Na, sodium metal, so it's positively charged, so it is actually electrophile. Electrophile means positive charge, looking or wanting negative charge. So this is electrophile. So it will be here the sodium propanoate, it will be an ethanol. As the alcoholic part is the same, but only the carboxylic part, where there is a carboxylic acid, there is a difference. Depends on the acid or basic medium it has been hydrolyzed. And this is one of the example that methyl propanoate, if it is started from here, what will happen in here, right? So this is the reaction that occurs. All right, so this is actually all it is today. Okay, and please go through the reactions. If you just look at the reaction, you will forget. You will think that you remember, but in the exam you will never, unless you rewrite it on the paper. This is one mysterious thing of chemistry, that if you read, you will forget. If you just read, look at it, you will forget. But if you do on the paper, write it, you will remember it. Okay, so please do. You need to do some practice. Okay, so any question, anybody? Anyone has any question? No? So I'll see you on Thursday during the lab, and please come prepared. Read through the manual. All right, at least 3 times read it. If you don't understand, let me know at the beginning of the lab so that we can discuss and start, and it will be smooth. Okay, another thing is,